Okay, so here's the problem that reads, find the equation of the tangent to the curve y equals x squared plus 2 at the point where x equals 2. And don't worry if this sounds completely unfamiliar, because this is the start to our next branch of differentiation, or rather the application of differentiation, known as tangents and normals. So, essentially, what is a tangent first? That's the first word that you can see over here that is kind of ambiguous. Well, let's take the curve y equals x squared plus 2 that we've just been given. I'm just going to do a very rough drawing. So let's say this is 1, 2, 3, 4, 5, 6. This is -1, -2, -3. This is 1, 2, 3, 4, 5. Okay, and if we draw the curve x squared plus 2, we can see it has a y-intercept of 2, and it's a parabola. Like that. It extends outwards. A tangent is essentially a line that touches a curve or any sort of like other line at one distinct point. So it can't touch it two. Like for example, this line here would not be a tangent because it's touching it at this point and this point. However, this line would be a tangent because it's only touching it at that point. So now that we know what a tangent is, we need to figure out how are we going to find the equation of the tangent to the curve y equals x squared plus 2 at the point where x equals 2. Well, if you visualize it, when it says x equals 2, that means we're finding the tangent where it lines up with the line x equals 2, which would be around here. So that would be look like a line. That would look like a line like that. So notice that I've drawn it as a straight line. That's because a tangent always has the equation y equals mx plus c. Basically just a linear function. And it's touching it at one distinct point. In this case, it's at x equals 2 as it's specified. And as we can see, the gradient seems to be positive of the line. So m, in this case, is positive, and it's quite steep, so it should be a pretty big number. So the reason differentiation is used here is because if you were to differentiate mx plus c, you would just get m, which means that by differentiating this function over here, we can find the gradient of this tangent. So let's do that right now. So differentiating y equals x squared plus 2, so dy over dx is equal to 2x, and the constant goes away. You might be wondering, well, this isn't a constant, this isn't our gradient. How do we actually find our gradient from here? Well, we're given the point x equals 2, so we substitute x as 2 in here, which is 2 times 2, which is just 4. So our gradient is 4, and we can check with this diagram. For some diagrams, it won't be so obvious because the curve will be very, very complicated. But in this case, we have drawn it out. And 4 seems to be correct because it's quite a large number. And the line over here is positive because it's going up as x goes up. So 4, we can say, is a pretty good guess. Now what we need to do is find the rest of the particulars of the line. And to do this, we first need to identify what exactly this point is, because otherwise we can't just start making the line go through it. Well, we can just plug in x equals 2 into the original curve, which is y equals x squared plus 2. When x is 2, y is 2 squared plus 2, which is equal to 6. So the point at which the tangent we're supposed to find the tangent at is 2, 6. And now we have the information we need to find the tangent. So our tangent is y equals 4x plus c, because as you can see, we already found the gradient over here when we differentiated the function. And now we just need to plug in 2 and 6. So 6 goes in y, and 2 goes in x plus c. And we have 6 is equal to 8 plus c. So c, by rearranging, is -2. And that's the equation of our tangent. It is, let me just write it out, y equals 4x minus 2. Which seems right, because if we were to continue this line along, it intercepts at a negative position, which is likely to be -2. And that's essentially how we find the tangent. We just differentiate the function, then we find the point of contact, and then we can substitute the values of x and y into our tangent function and find the value of the y-intercept. And that's our answer. Okay, let's look at another problem now. Okay, so let's look at this problem. Find the equation of the tangent to the curve y equals x cubed plus 7, all divided by x plus 1 at the point where x equals 2. So I know in the last question I found the value of y at the point x equals 2 after differentiating it, but I think in this case it's probably more logical to just find the value of y now. So let's just substitute x into the equation. So that gives us y equals 2 cubed plus 7 over 2 plus 1, which is equal to 15 over 3, which is equal to 5. So our gradient is 5 in this case. Obviously, you can't draw this one because it's not going to be such an easy curve to draw, but with the correct working, we can be pretty certain that our answer of 5 here is correct as our y value. So it's 2, 5, the point we're looking at. And you also have to just trust that your differentiation is correct and your gradient is correct when you get it, because you're not able to visualize it like in the last problem. Now we can differentiate it. In this case, we can use quotient rule. So we can do y is equal to, and then I'm not going to write the quotient rule out, but I'm just going to start differentiating it. So dy over dx is equal to x plus 1 times 3x squared minus x cubed plus 7, which is all divided by x plus 1 squared. In this case, you don't actually need to simplify further because you're just going to substitute your value of x in right now. You're not trying to simplify this down. When you substitute x into there, you get 2 plus 1, which is 3, times 3 times 2 squared, which is 12, minus, and then 2 cubed is 8 plus 7 is 15, minus 15 divided by, and then it's 2 plus 1 squared, so that's 3, that's 9, which is equal to 36 minus 15 over 9, which is equal to 21 over 9, which can be simplified down to 7 over 3. So in this case, our gradient is going to be 7 over 3. And now we can just substitute it into the gradient formula. So we have y equals 7 over 3x plus c, and we can just substitute x and y in from over here. So x equals 2 and y equals 5. So 5 is equal to 14 over 3 plus c. So c is equal to 5 minus 14 over 3, which is equal to 1 over 3. So our answer is y equals 7 over 3, 7 over 3x plus 1 over 3. Let's look at one last problem before we wrap up this video. Alright guys, so here's the next and final problem. Find the equation of the normal to the curve y equals 4x ln x at the point where x equals 1. First thing we have to notice is that we have the word normal in there, which is not the same as tangent. And it must be pretty significant. So let me just take the old example of x squared plus 2. So that's kind of what the graph looks like. So I'm not going to draw the scale. And the tangent at x equals 1 looks something like this, where that's the point where x equals 1. The normal would look something like this. And you may have noticed that the tangent and the normal are at 90 degrees. So essentially, the normal is the perpendicular version of the tangent at that exact point. It does not necessarily touch the curve at one point because it is perpendicular to the actual tangent, which only touches the curve at one point. So what do we do differently? Not really much. It's pretty much the same. So we do the first few steps at least exactly the same. So we first find the value of y, the y coordinate of this point. So y is equal to, and then we just put x into the curve. Y equals 4 times 1, which is 4, times ln 1, which is equal to 4 times 0, since ln 1 is just 0, which is just equal to 0. So we're working with the point 1, 0. We can leave that there and come back to it. Now we differentiate the function. So dy over dx, which if you remember is the notation for differentiation, is, and we can use product rule. I'm not going to write the rule out again. So we first differentiate the 4x, which would give us 4, and then we multiply it by the ln x. And then we add it to the differentiated version of ln x times 4x, which is 4x over x, which can be seen as 4 ln x plus 4. And now we substitute the values of, we substitute 1 into the value of x we're given, which in this case is over here. So we get 4 ln 1 plus 4 to get our gradient. 4 ln 1, as we established over here, is just 0. So we have 0 plus 4, which is 4. So our gradient at this point is 4. So until this point, we've been doing pretty much the steps needed to find the tangent, but we need to find the normal. And we need to, basically we can tell that if we have the tangent and the normal is perpendicular to the tangent, the gradient has to be the negative reciprocal of the tangent's gradient. So in this case, the normal's gradient would be the negative reciprocal. So that's, we flip 4 over, makes it 1 over 4, and then we negate it, so it's negative 1 over 4 now. So our gradient is negative 1 over 4. Now we just input that into the standard y equals mx plus c tangent formula to get y is equal to negative 1 over 4x plus c. And now we input x and y from over here to get 0 is equal to negative 1 over 4. So c is equal to 1 over 4. So our final answer is y is equal to negative 1 over 4x plus 1 over 4. And that is the normal to the curve. I'll attach some worksheets below for some practice. In the next video, we'll go over some external points, which I'll cover more in detail when I do the video. And until then, thanks so much for watching and see you in the next one.